Hi students, today we will see a very important reaction in organic synthesis, that is Diels-Alder reaction and also the related reactions. Let us see the introduction part. In a Diels-Alder reaction, 1,3-diene reacts with dienophile to form a 6-membered hydroaromatic ring. In this reaction, the product contains 2 new sigma bonds and a new pi bond. This is also an example of cycloaddition reaction. The reaction takes place very easily with moderate application of heat. In few cases, Lewis acid catalysts are also used. Let us see some of the examples of Diels-Alder reaction. The first one is diene. Butadiene reacts with ethylene to form cyclohexene. Second example, butadiene reacts with ethine to form cyclohexadiene. So in all the three reactions, a diene reacts with dienophile to form a cyclic adduct. Now let us see some examples of dienophiles. Ethylene and simple olefins are poor dienophiles. Most dienophiles are in the form where Z and Z dash are CHO, COOH, COR, COCl, COAR, CN, etc. So Z and Z dash are electron withdrawing groups on the dienophiles. Sometimes the dienophile itself acts as a diene. Triple bonded compounds also act as dienophiles. The dienes should be in the cis-oid form and not the trans-oid conformation. In this particular example, we can see two forms of butadiene. One is the cis-oid form in which the two double bonds are cis towards each other, and the transoid form in which the two double bonds are trans towards each other. Now let us see two examples, butadiene and the dienophile to form the cyclic adduct. Here in the first case, butadiene reacts with the ethylene compound, and in the second case, butadiene reacts with the triple bonded compound. Then this is also an example in which the dienophile is a cyclic compound. Similarly, the cyclic compounds, both diene and dienophile are in the cyclic form to give the very complex adduct. So these are the various examples. In the diene, electron releasing groups will increase the rate of the reaction. And in the dienophile, electron withdrawing groups will increase the rate of the reaction, and vice versa. The usefulness of the Diels-Alder reaction in synthesis is due to its versatility and remarkable stereoselectivity. By varying the nature of the diene and dienophile, different types of ring structures can be constructed. Heterocyclic compounds are also obtained. Now let us see the mechanism of Diels-Alder reaction. The rate determining step in adduct formation is bimolecular, and the two components approach each other in parallel planes, roughly orthogonal to the direction of new bonds. Now there are two main views regarding the mechanism. Number one, concerted mechanism. Two new single bonds are formed. At the same time, there is a cyclic 6-membered transition state. There is no intermediate. This is the first view regarding the concerted mechanism. Then two-step mechanism. In the two-step mechanism, the first step involves formation of a single bond between atoms of reactants, and it is a rate controlling or rate determining step. The second step, addition, is completed by formation of second bond in the fast reaction. The intermediate is either a Zwitter ion or diradical character. Evidences for one-step mechanism. The reaction is stereospecific with both diene and dienophile. A completely free diradical or diion probably would not be able to retain the configuration. Diels-Alder reaction depends very little on the nature of the solvent. These rules out diion intermediate because polar solvents increases the rates of reaction that develop charges in the transition state. It has been shown by Seltzer that bonds A and B break simultaneously in the adduct. Therefore, according to the principle of microscopic reversibility, forward and reversible reactions will also follow the same path. For a two-step mechanism, the reaction involves a radical or ionic transition state. In such case, the ring closure will require additional activation energy. If the intermediate is longer lived, then the rotation about CC bond will yield non-stereospecific products. In this connection, addition of Lewis acid improves the yield of Diels-Alder reaction. This suggests that cycloaddition is concerted. If it is concerted, not be necessarily synchronous, depending on the types of dienes and dinophiles, the reaction may be synchronous or non-synchronous. The two-step mechanism is not completely ruled out. If rotation about CC single bond is slow when compared to ring closure, example, cycloaddition of cis and trans 1,2-dichloroethylene to cyclopentadiene is completely stereospecific. A two-step mechanism would result in the diradicals, which might be long-lived, to undergo interconversion, resulting in a mixture of bonds. Though a Diels-Alder reaction, it may be a synchronous or a non-synchronous reaction. In a non-synchronous reaction, both the bonds begin to form at the same time, but the process may take place at different rates, and one bond is formed to a greater extent when compared to others. An unsymmetrical transition state is involved. In a synchronous reaction, both the bonds are formed at the same time and both are simultaneous. So the Diels-Alder reaction may be a concerted non-synchronous reaction or a concerted synchronous reaction. So this is about the mechanism. And in the next class, we shall continue catalysis by Lewis acids in a Diels-Alder reaction.